Okay, so shall we start? Love. Okay, so as always, let's start with the review. So what were we talking about in the previous class? Any idea? Okay. We talked about uh, the vector form of Gauss law. We were studying Gauss law. We have already studied the scalar form of the Gauss law. We saw how things changed in higher dimensions because we need to introduce vectors, and then after that,
So, one
okay,
minute.
go ahead.
So, first we started with electromagnetism. Then
Yes.
we went to quantization of charge,
Mm.
and then we came to Coulomb's law. And the
Mm.
Coulomb's law was थोड़ा सा छूट गया था. Then afterwards we came to Guess law.
Oh,
This one
yes. 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 We
in
talked about the
vector form.
scalar version of the Gauss law first in one dimension, and then we generalized it to higher dimensions, two-dimensional problems, three-dimensional problems, and we
Yes.
realized that we need to use vectors in order to come up with how essentially these force fields act. Then we
So ये
talked
वाला
about,
तो मैंने किया हुआ है vectors और Guess law वाला.
yes. We're just reviewing everything, right?
Oh, okay. Yes.
Okay. So after that, we collected a bunch of objects. So the vector form of the Gauss law is for one particular particle. Then when we try to
Yes, sir.
generalize
Then we
that
did
as well,
superposition principle.
absolutely, we talked about the superposition principle.
And then we came to equilibrium.
Yes. And then we talked about equilibrium.
Yes, sir, that's it.
And then we did a couple of problems on equilibrium. The problem that we tackled was a one-dimensional problem where you had two charges, a charge E and a charge 4 times E, and we wanted to figure out what was the equilibrium point. If you had a test charge which was kept in the middle, what is the point of equilibrium, right? So let's continue
Yes,
on
sir,
that.
that was A by 3.
Yes, the answer was A by 3. Absolutely true. Now let's continue on the same path as we were already doing, and let's talk about a two-dimensional problem where you have to do similar things. So let's imagine a square. Okay, let's imagine a two-dimensional square on the edges of which, or not on the edges, on the nodes of which, on the vertices of which, you have four charges. Let's say let's name them first. Let's call this A, let's call this B, let's call this C, and let's call this D. Okay. Let's say you have charge Q on A and you have charge capital Q on C as well. Now, let's imagine on B you have a charge minus Q that is kept there, and on D as well you have the same charge minus Q. Now, what should be the question is what should be the sign of the magnitude, sign of the magnitude of the ratio q small, apologies, small q over capital Q, so that first the net force, the net force on capital Q is 0, and secondly the net force on small q is 0. Does the question make sense?
So, what charge do we have on the point C?
I'm sorry?
So,
Can you say?
what is given under? Okay.
This is also q. So you have q at A and C, and small q with the negative sign at B and at D. Okay. So go
Yes.
ahead. Try to apply Gauss law here. Try to see how the vectors are essentially evolving. Just spend a couple of minutes on this. Let me also give you the side, which is distance A. Let's say.
So these two things, that the net force on Q is 0 and the net force on small q is 0, are given as conditions, or we have to prove.
Yes. So these are conditions. This is the first condition and this is the second condition. So for this condition, in the first part, the net force on capital Q is 0. What you need to find out, what will be the sign of the magnitude so that the situation arises.
Excuse me, sir.
Yes, go ahead.
So I just have a thought that one, when we are talking about net force on Q is 0 is given. That means the force acting from point B to A is same as force acting from point C to A,
Yes.
and this same
And D to
and
A as
this
well.
from this will, yes, sir, D to A.
Yes. Sorry.
So, sir,
Hmm.
from this we can get that minus Q charge is uniform on both the sides that is being acted on the weak charge.
Okay. Okay.
So,
Okay. So let's think about this. Let's think about this for a second. So um, let's consider the charge placed at A. Let's see all the forces that are acting on this charge. So first of all, you have B. B is a negative charge, so it has a negative sign, and Q is a positive charge. These are opposite charges. So in what direction will you expect the force to be acting on Q because
opposite
of which?
direction.
In the opposite direction or in the same direction? Like charges are
Sir, opposite
repelling,
direction.
unlike charges are attracting, right? So
Yes.
unlike charges attract. So there's a negative charge and there's a positive charge, so they'll attract each other.
So they'll
Sim-
come towards each other.
yes, exactly. Similarly, in this Q, because of this D, there will be a force that Q will have in this particular direction, and because of the Q, which is on the diagonal, you will have another force which is acting along the diagonal but away from the center. Now, there are three forces acting on these. When you want to find out an equilibrium point, what essentially do you have to do? You need to make sure that along the x-axis and along the y-axis, or how many ever axes you have, the net force is zero, right?
Yes, sir.
Okay, let's do that then.
So, sir, this means that this would mean that along this at the particular point Q,
Hmm.
as the net force is 0, so Q is the equivalent.
Q is the
equilibrium for each and every force which is acting on it. So resultant will be zero.
the resultant will be zero. No, wait. Okay, so this is distancing. Let's apply Coulomb's law here, right? So because of the force on A, because of B, let's just calculate this. This is going to be just K times capital Q times small q over R squared, which is A squared.
R square, which is A square. Yes, sir.
And this is in what direction? It's in the direction of positive. Let's call this direction as I cap. So positive x direction as I cap and positive y direction as j cap. Okay.
J cap.
So this vector will be k q capital Q small q over a square I cap. Correct.
Yes, sir.
Now, the first, because of D, AD is going to be very similar. It's going to be KQQ over A square, same exact magnitude, but what direction is it acting
J
in? It's
J
acting in
J
minus J cap, correct?
J cap. Minus J
Minus J
cap.
cap, because it's downwards. Now,
Oh, yes.
what about the first because of C? A on A because of C. Well, what is the distance between these 2 points?
Sir,
Well,
root 2A.
yes, exactly. If the side is A, then the diagonal is A times root 2 because it's a 1 root 2
Yes, sir.
uh, right angled triangle.
So, sir,
Uh,
2A square.
so you will have K times Q squared over 2A squared, correct? But in
Yes,
what
sir.
direction? In what
So
direction?
this will, sir, I guess both the charges are like charges, so they will go in as the same direction. So they will act in the, what do you say, negative z direction, z cap.
No, wait. So if you have a vector which is acting in some random directions and you have the axes, so essentially what you need to do is you need to resolve the vectors along these axes, right?
Yes, sir.
So how do you resolve? Well, this angle, we know since this angle is 45 degrees, it has to be 45 degrees, right? Because this is 90
Yes.
degrees and cutting it into half makes it 45 degrees. So this angle is also 45 degrees,
So cos 45,
which is 1 by root 2,
cos
right?
45. Yes, sir.
So you'll have I cap over 1 by over root 2 plus j cap when you do the sine of 45 degrees, which is also 1 by root 2. So
Also
you'll
1
have
by
over root 2.
j by
Correct.
root.
Okay.
Yes,
So
sir.
now all you need to do is just compare what is happening along the x axis and what is happening along the y axis. That is all you need to do now. So x axis के along क्या क्या है? You have along the I cap you have this fabulous. Oh, just a second, our signs are not correct here if we haven't noticed. This I cap is actually a negative sign because this is in the backward direction, correct? In the left,
Yes, sir.
there has to be a
Yes.
negative sign there as well. So keep in mind all these directions and signs. All of these are super important because otherwise your answers will not work. So let's see what is happening along the I cap direction. What is happening? The F net, the net force is KQQ over A squared, which is the positive x-axis, and minus KQ squared over 2A squared times root 2, right? Now, if this net force has to be equal to 0, which means Q is in equilibrium, then what do you have? Let's solve this. You have the K's cancel out, one of the Q's cancel out, the A square also cancels out, and what you have is you have Q minus capital Q over 2 root 2 is equal to 0. This implies Q over capital Q is just 1 over 2 root 2. Make sense?
Uh, so q minus q upon 2 root 2
Hmm.
is equal to 0. Yes, sir.
Yes. Does this make sense?
Totally, sir.
So all we did was essentially just compare what is happening along the x-axis. but our job is not done yet, is it? We still have to figure out what is happening along the y-axis, because if the net force is zero, it has to be zero along both the x-axis and the y-axis. So let's do that as well. uh, where do you have, okay, let me just start this. Okay, what is happening in the j direction? Yuvraj, is it okay if you turn your video on,
Yes, sir.
please? Thank
Sir,
you.
I don't, sir, I turned it on, but मेरे को लग नहीं रहा कि यहाँ पे चल रही है.
Okay, no worries, no worries. Okay, so let's see what is happening along the j direction. Well, along the j direction, you have FAD and one of the components of FAC, correct? So the net force here along this direction, it's going to be KQ small q over A squared with a negative sign, plus KQ squared over 2A squared root 2, which is going to be equal to 0. Now, notice again, your KQs cancel out and your A square cancels out. And what you get is exactly the same condition. It's again Q over Q is equal to 1 over 2 root 2.
Sir,
This,
but other,
uh,
we just get minus q over here. Minus q plus q upon 2.
yeah, so it doesn't matter, right? It's still a minus sign overall. See,
Yes, sir.
it's so you can just take the minus sign common out, and it's still the same.
Yes, sir, yeah. Got it.
And since it's equal to 0, the minus sign doesn't matter. So that's why it's exactly the same answer. So a lot of times this will happen. What one expects is that the number of variables and the number of equations, if they're absolutely equal, you will be able to solve or for all the variables. You should have been technically able to solve for q, small q and capital Q here. But many a times what happens is that when you're solving two equations, they essentially turn out to be the same equation. So
Yes, sir.
if you'd like to, if you go back in your matrices chapter in class 11th, you would remember how essentially when you're trying to solve linear equations, so number of variables and number of equations from there. A lot of times what happens is that two equations just have one thing in common and they're exactly the same equation. Exactly the same thing is happening here. We have two equations that are exactly the same equation, and this happens. It's absolutely okay. Whatever you were asked, you have calculated already. Now, could you do all of this again for a small q, for let's say the charge at B, let's say this exercise that we did
For the small, for
yes
point B.
for point B, yes, absolutely. Is it making sense?
Sir, when if we take the B point,
Hmm.
the magnitude will be the same for FB of A and FB of C. But we just observe that J cap turns out to be positive and I cap turns out to be negative.
Yes, absolutely. And what will essentially happen is when you do the calculation, your 2 over root 2 will just shift to the small q. So essentially, the ratio q over capital Q here, when we're calculating for the first part, we're getting 1 over 2 root 2. In the second part, you'll get 2 root 2. Okay, so
Okay.
for the second part you will get q over q to be equal to 2 root 2. Just do this once, check if your calculation is absolutely correct, and if it is correct, this concept is absolutely clear. Okay,
Yes.
so let's move on. Let's move on to a slightly more generalized a more generalized way of doing exactly what we're doing. We're essentially, if you think about it, using the superposition principle, right? We have multiple charges, and what you're doing is you're using Gauss law for every single charge, and you're just adding up the total amount of force that is acting. It's just the superposition principle in practice. Now, what if we now end up having continuous objects? Let's say we have a rod. Okay, so we have a rod with some charge density lambda. When I say charge density, what do I mean? I mean, if you take the total charge on this whole thing and if you divide it by the length, so let's say the length is capital L, that ratio we'll just call charge density. Similarly to this, if we ever, we'll soon talk about sheets of paper as well, sheets of, sorry, charged charge sheets as well. There you will have again a charge density which we denote by sigma, which will be just your total charge on the sheet divided by the total area. Okay, and when we're going to talk about three-dimensional objects, we're essentially going to define capital rho as the charge density, where we'll define it as the total charge on this three-dimensional object over the total volume. Does this make sense? This is just notation.
Yes, sir.
Lovely. So let's start with the one-dimensional case. Let's again say that there is some charge
Sorry,
on this.
internet picture results.
I'm sorry.
Sir, can we go on to the previous page for one?
The previous page.
Yes, sir.
Yes. So let's this
Well,
the total area will be this much, and the total volume.
okay, sir. So that is for 2D and the other one is for 3D.
3D, exactly. So just remember these symbols. These symbols are essentially what will help you distinguish between what kind of a problem you're dealing with. Okay.
And sir, what is Q in this
Q
formula?
is the total charge on this whole object. So if it's a one-dimensional rod, the total charge on the rod is capital Q. Or if it's a sheet, the total charge on the sheet is capital Q. And if it's a volume, the total charge in the volume is capital Q. Okay.
Okay, sir. And what about the sigma lambda and all?
So these are the densities. So this is the linear density. This is the surface density. And this is the volume density. And इसमें हर जगह charge add कर दो. So this will become linear charge density, this becomes surface charge density, and this becomes volume charge density. Okay,
Yes, sir. Done.
makes sense. Lovely. Now let's talk about the simplest case. Let's talk about the one-dimensional case, where you have, let's say, a rod with the total charge capital Q, so and length capital L. So let's say charge capital Q, length L. So this is just Q over L. Now, what we need to find out is that on this axis, let's say you have a point here. Let's call this point capital P. Let's say this point is some r distance away. from the beginning of the rod, what we need to find out is what is the net force F net at P. Okay. Now, up till now, what were we doing? We had discrete objects and we were adding them up. When you have continuous objects, what do? You integrate, right? So, how are we going to do that? We're just going to say that let's take an element, small element here, dx. Okay, and let's say the distance from P of this dx element is some x. Okay, so this distance from here to here is some x. So if I find out what the force because of this small element charge is acting on this, then I can add up all the elements and calculate the net force, right? That is the essential
Yes,
strategy we are going to use. That is the strategy we are going to use. So let's say, so the small amount of force that is acting because of the small amount of dx object. Now, this object which has length dx, how much charge will this dx have?
so uniform charge as equal to what the other thing will have.
Yes. So what you're given is the charge density, which is lambda, correct?
Yes,
If you multiply the charge density with the volume, or in this case, if you multiply the charge density with a particular length, you'll get the charge inside that length, correct?
yes.
So what I'm saying is that this dx, the amount of charge dq that is in this, is just going to be lambda times dx, right?
Charge density into length. Yes, sir.
Another way of seeing this is just noticing that when I'm writing dq is equal to lambda over dx, all I'm saying is that lambda is just dq over dx, right? Which is just the rate of change of charge, or with distance, obviously. Or if I write the total charge, this is the small charge, this is a small distance. If I write q over l, which is essentially this is also lambda. So that is how essentially you can see this. It's still the ratio of a small thing over a small thing, or a big thing over a big thing, a total charge over a total length, or a small charge over a small length. It's still the same ratio. That's how you can see this. Okay, so now what is the force that is going to act at point P, this unit test charge that we have kept at point P? Well, it's going to be according to Coulomb's law. It's going to be K, which is 1 by 4 pi epsilon naught times, um, let's say this is a unit charge. So let's say this has charge 1. This has just 1 coulomb of charge. So a test charge has 1 unit charge. Okay, so you have dq, you have the one charge over, what is the distance? The distance is x. So you have x
X.
here. Lovely. So now notice you have a df here and a dq here. So what you're doing is absolutely fine. Now all you need to do is just integrate. Is just add over these small parts. So let's do that. Let's integrate on both sides. But what are the limits going to be? Well,
Sir,
well, let's think about the lower limits first. The lower limit is from point here. So from point here, this is distance r. What is the force going to be? Well, there is no charge there, so the force is going to be 0 because it's starting there, right? And
yes, sir.
till where it's going to go? It's going to go up till r plus l, correct? Till the other end. So
Yes,
it's
sir.
starting from here and ending here. That's all essentially we're doing. And what is the total force going to
Sir,
be? It's
R
going to be the
plus
F.
L.
Huh?
If you're starting from there and ending there, would it be simply L? If I would be say that it starts this.
Bacha, because we're starting from P. We're not
Yes,
starting
sir.
from here. So this is R. You need to add this length also, right? So from
Because
here,
we just took R because we know that that is the point from where the charge started. So that's the lower limit.
okay. So depends on where you're focusing. So here you're focusing on point P, right? But the force is because of this distribution of charge, which is a rod right now. The rod starts at R with respect to P. We are always writing things with respect to P. It's starting at distance r and it's ending at distance r plus L, right? So this distance from P is this distance, which is L, plus this distance, which is r. That is all I'm writing. It's a very, very simple thing I'm doing, right? So let's do this integration on both sides. Um, well, right now we cannot. Can we? Can we integrate the right hand side? We cannot directly integrate the right hand side. Why can we not? Because Q is a function of x, right? Q is
Yes.
change. Q is a function of x. So you cannot. So right now, what you need to do is write dq in terms of dx. How do you do that? Well, we've already figured out how do you do that, right?
Lambda dx.
So let's just substitute this here. So this right hand side becomes, so this is just the right hand side that I'm writing here. This becomes an integral from r to r plus L k lambda dx over x squared. Make sense?
Yes.
What's the integral of 1 over x square?
Sorry, sir.
What is the integral of 1 over x square?
Sir,
Yes. So what's the integral of 1 over x square? Let's no need to no worry. So 1 over x square dx. Just need to integrate this. Well, well, let's talk about it generally, right? We know what happens generally. We know that x to the power n, if you want to integrate, this is just x to the power n plus 1 over n plus 1 plus a constant or a constant of integration. So if you put
so
n
sir,
is
it
equal
will
to
be
minus 2,
sir, it will be x raised to power minus 1 upon minus 1.
absolutely.
Uh,
So you'll have integral of x to the power minus 2 dx to be equal to x to the power minus 1 over minus 1 or just minus 1 over x.
Minus 1.
Lovely. So the integral of 1 over x square is just minus 1 over x. So let's do that. Let's put in the values. You have k lambda over x. From where to where? From r to r plus L.
R plus L.
Let's put in the limits also. So you have 1 over r plus L minus 1 over r. Okay.
Yes.
Now notice that r plus L is obviously greater than r, right? So
Yes.
1 over r plus L is going to be smaller than 1 by r. See,
Yes,
if
sir. Got it.
see 3 is greater than 2, this implies
Yes,
1
sir.
over 2 is greater than 1 over 3. That is all I'm saying. So
Understood. Yeah.
essentially what I'm saying is that the negative sign inside the bracket will dominate. So the inside the bracket, whatever you will have will be negative. So I can
Will be
take the
negative.
negative sign out. So I can just write this as k lambda 1 over r minus 1 over r plus L. And you can simplify this further on. You can take the two things together. You can write it as r plus L minus r, or L over r into r plus L. So you can combine the two. You can play a lot of games with this, but this is what your final answer will be. So this is essentially how you progress. You take small elements, see how far away it is, and add
Yes.
up all the elements. Okay.
Yes.
Does this derivation make sense? If this makes sense, let's try another derivation of this time a ring. Okay.
Yes.
Okay. So apologies. Just a second. So let's think of a ring, and let's think about so this line that I've drawn here. This is going through the central point. through the central axis of the ring. Doesn't look like it, but it sure is. Uh, Now, what you need to find out is on this axis, let's call this point P. Let's say this point is some r distance away again. And let's say the radius of this circle is some capital R. Okay. The question is, what is the net force on this point P, which is on the axis?
So here it is given that the distance is r and the radius is capital R.
Yes.
So sir, the force should be
Okay. As previously, let's first. Okay, I have not yet completed the question because your first question should be: there is no charge here. Where is the force coming from? Correct.
exactly that's what I was wondering.
Okay, so let's say there is some linear charge density lambda on this whole ring, which essentially means that the total charge is capital Q, and the total distance is 2 pi capital R. So lambda is just Q by
So sir, we can conclude that the so for taking out the charge on P,
hmm,
what we can do is
the
we can
charge at
conclude
P.
that
No,
the
no,
point
not the charge at P. The force at P.
yes, so the force at P, we can
Uh,
conclude that the point which is the center of the ring is the
hmm,
equilibrium. So charge
hmm.
there will be zero, and
Yes.
hence we conclude that the distance r
Uh,
from if we take this point on the ring as A and center point as B,
hmm,
so A to B will be zero. Force from A to B.
hmm.
So we
But
have
you have
lambda,
some
which is
charge
the
here,
total
right?
charge.
But you have some
Yes,
charge here, and you have some charge here. So if
yes, sir.
I draw this line from here to here, there is some force that's going to act along this line, right?
Yes, sir.
Let's say it's acting along the outer line. But not only that, similarly, you'll have a line which is coming from the opposite end, right? And it's
Yes, sir. So
crossing.
it would cancel out, right?
Only the y direction will cancel out, but the x direction will remain, right?
Oh, yes, sir.
Yes, absolutely. So, what essentially what you said is exactly correct. So let's call this angle some theta. If this angle is theta, this angle is obviously also theta. This angle is also theta, and this angle is also theta. Your opposite angles and blah 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 blah. Well, what is? How do you figure out what this angle is? Well, you know this distance r, you know capital R. You see that this is a right angle triangle. So you can also see that tan theta is just going to be my capital R over small r. Correct?
Yes, sir.
Yeah, simply because of this right angle triangle existing in this plane. Okay, so now from as you already said, from symmetry considerations, because you have a charge here and also a charge exactly on the opposite side, the y component of both
Will
of
come
these will
become
cancel out. So the y components, the Fy will essentially be equal to zero. The net force along the y-axis is going to be zero. Why do we say that? Because of symmetry considerations. That's it. Now, along the x-axis, however, what is the force because of this small element here? Let's call this element some dx. How much charge does this element now have? It has some dq charge, which is equal to lambda times dx.
so lambda dq. Yes, sir. Lambda dx. Sorry.
Lambda times dx.
So dq is a small element on the ring, right?
Yes, dq is a small element on the ring.
So why do we take it as dx? Like, cause the length of the element is very small. That's why.
Yeah, small. We're taking small length. Yes, absolutely. That is why.
Okay, sir, but isn't it the differential of distance dx?
Hmm?
Sir, but isn't dx the differential of distance?
Yes, it is. But so what's the point? I don't understand what the problem is.
Sir, I was just asking, like, when we take a element on the ring,
Hmm.
because its length is very small,
Ah.
so that's why we take it as dx, because
Yes,
dx is a very small quantity.
yes, absolutely.
Dx is also the differential of length.
Yes.
So, what do we want to say that the element has a bit bigger length, but we want to take the part of the element, the
No, no,
dx,
no,
the
no,
differential
no.
of
All we are saying is that we're taking a small element and we're just calling the length of this element as dx. Why dx? Because dx is denotes something tending to zero. That's it.
okay.
It's just a notation. There's no uh, there's no further outlook on this.
And sir,
Okay.
how did we get the value of lambda q over 2 pi?
Well, lambda. What? How is lambda defined? Lambda is the total charge over the total length, right?
Yes, sir.
Let's say the total charge is q. Uh, let the total length is just 2 pi r.
Oh, okay.
Make sense?
Yes.
Lovely. Okay, so let's see what is happening along the x-axis. Well, the small, just write it down here. Okay. So small f, so this is along the x-axis. This small differential along the x-axis, because of the small thing here, will essentially just be your k times the charge that is there, which is essentially just lambda dx, or let's just still write it as dq here. Keep it as dq here. But okay, dq, then you have a test charge there, so 1 coulomb there over what is the distance from this point to this point. Well, again, this is a right angle triangle, so you can use Pythagoras theorem to essentially
Sir,
figure it
r
out.
square plus small r square under the root.
Absolutely true. Capital R
So,
square
sir,
plus.
this will be directly r square plus r square.
Yes, but however, it's not over yet, because you need to take the x component of this vector. This is the force which is acting along this direction, right? Along this direction,
Yes,
sir.
so it would be sine cos of x, so cos
Cos
theta.
theta, cos theta, absolutely.
Yes.
Now, let's. Okay, things are being weird. Okay, so let's substitute the values. Mm. So, okay, so now you have cos theta. You know tan theta. You know tan theta is r over theta, but what is cos theta? Well, you know how to convert tan theta into cos theta, right?
Yes.
How do you?
So by multiplying it by, sorry,
No,
so
no,
by
no,
multiplying
no.
it by 1/2
इतना दबाग नहीं, just square both sides and add 1. That is all you need. Let's do it. Tan square theta is equal to r square plus r square, correct?
yes.
Adding 1 to both sides, you get 1 plus tan square theta is equal to 1 plus r square over small r square, correct? 1 plus tan square theta क्या होता है? Sec square theta
Cos
होता
square,
है. Sec square
sec square theta, sorry.
r square over small r square. This implies 1 over cos square theta is just equal to r square plus small r square over small r square. This implies, if I remove all of this implies that cos theta is nothing but r over the square root of r plus capital R. Hello, Yuvraj. Apologies, the internet just went off.
Oh,
Can you help?
no sir,
Can you help?
मुझे लगा वेबसाइट पे कुछ है क्योंकि मेरे साथ पहले भी हुआ हुआ है वेबसाइट पे.
Huh? I'm sorry.
Sir, I thought it was something to do with the website because prior also it once happened with me.
No, no, no. My light went off here, so the internet also went off.
No issues.
Yes. Sorry. Where were we? Okay, we were. Okay.
So we completed that thing, the round one, the ring
The,
one.
so is we have not yet completed it. We just
So
wrote
we concluded that the cos theta is equal to r by under root r plus capital R.
cos. Yes. Cos theta over square root of r square plus capital R square, and cos theta we figured out it to be small r over square root of r square plus capital R square. Is that correct?
Yes.
Lovely. So let's put in the values here. Oh, apologies. This is not a square root here. This will not be a square root here because it's r square, right, in the denominator. Sorry,
Yeah.
L square.
Yes, sir.
Okay, so now let's put in the values. Okay, so this is k times lambda dx r over square root, uh, actually 3 over 2 power r square plus r square to the power 3 over 2, right? Now you need to integrate this from where to where? Well, from 0 to 2 pi r, 2 pi capital R, correct?
Yes.
So let's do that. Mm, there's well, notice all the things that you have in here: k, lambda, small r, and capital R. All of them are constants, so all of them can be taken out, right? K
Yes,
lambda
sir.
small r and small r square plus capital R square to the power 3 over 2, 0 to 2 pi r dx, which just equals to 2 pi r. The integral is just 2 pi r, right? So this is just k lambda r times 2 pi capital R over r square plus r square. Does this make sense?
Yes, sir.
Love. Okay, so if all of this makes sense, then we have a decent grasp on essentially how the superposition principle is going to work and how this integration method is going to work. So this what we did up till now was essentially a warm up for the things, kind of things we're going to tackle in the future. Okay. Now, moving on to the next topic, let's define something that is called an electric field. Have you ever heard of the term electric field?
Yes, sir.
What do you mean by electric field? First of all, what do you mean by a field itself? What is a
The
field?
field is a certain area of coverage.
A field is an area of coverage. Okay, so there is a there's a very easy way of understanding a field. There is a very technical way of understanding a field, which is how mathematicians deal with it. Forget that. Nobody's dealing with that. But there's a very easy way that physicists essentially deal with the word field. It essentially just talks about space. So you have any kind of a space here, and at every single point on this coordinate, you have a value. So for example, let's think about temperature. So every point in space, there is a certain value of temperature, correct?
Yes.
So that is a temperature field. So all an electric field is saying is that every single point in space,
Will have the same charge.
no, will have a constant value, will have a
Oh,
constant, and that value will essentially denote the electric field. The electric field. So what an electric field is, it's just a number. Electric field is a number which is defined at every single point on space. It's just a number. Abhi tak it's just a number. How are we defining that number? We'll come to very soon. But a field is just a number that is defined at every point in space. Make sense?
yes, sir.
Okay. Fields can also change through time as well. So such fields will be called as time dependent fields when we'll come to them later on. Okay. So how do we define an electric field? Well, we actually, if you think about it, we have already defined electric field when we were calculating the force because of this rod or the ring on a test particle. Why is that? Because electric field is just the force due to a charge distribution on a unit test charge. So essentially, the force that we had, if I put my force is if it's equal to q over r squared, and you have one charge capital Q here, or a charge distribution, let's say some weird distribution cap which has some charge capital Q, and there is a charge small q here, and if you calculate the force on small q because of capital Q and divide this by small q, what you get is the electric field. So ये unit charge बन गया. So it's force per unit charge. Does that make sense?
So R square upon Q again.
Yes. So this q and q cancels out, and all that remains is kq over r square.
So, but wouldn't they multiply? Because this is divided by R square divided by Q, so Q will go up.
No much. So there has to be one more. So if there was divided by 2 here, then this would go to the numerator and this would go to the denominator.
Oh,
So this is how it goes,
okay.
right?
So,
This
so
goes
sorry.
here and this goes. No problem. No problem. No problem. No problem. So these two will cancel out, and this is just give you kq over r square. So that's essentially how we're going to define an electric field.
Then,
Should I go back?
no, sir, no.
Okay, so let's imagine this charge plus q here. We realize that the force that we were talking about, which was k, q, let's consider a lot of chest charges just kept at this radius, let's say r, on a circle of radius r, kq over r square. We notice that this is purely a function of the radius, right? So that just means that at some distance r, no matter what the angle is, it is independent of angle. Note, it is independent of angle theta. अगर मैं यहाँ पे इसका अब चार्ज मेजर फोर्स मेजर करूँ, यहाँ पे फोर्स मेजर करूँ, it should be exactly the same. So it is independent of theta. It is only dependent on r. So similarly, your electric field will also be only dependent on r. It will be exactly of this nature. So how will you define it? You will define it as the space around a charge in which the electrical properties, by which I mean the force because of the charge, the Coulomb force because of the charge that we've been talking about. Those are the electric properties that I'm talking about, can be experienced. Okay, so it's the space around a charge in which the electric properties or the force can be experienced.
Done, sir.
Okay, so now it's pretty clear from here that the electric field is is what do you say, is a fundamental property. Yes, is a fundamental property of charge. So it's like the sphere of influence of a charge. Wherever you will have an electric field because of charge, that will essentially be the point until where the charge is influencing other objects if you keep them there, or other charges if you keep them there. So it's essentially it's invisible. It's absolutely invisible until unless you put an external charge or a test charge inside the electric field. So as we said, we defined the electric field as the force. So this is also a vector quantity. So both of them are vector quantity. But we'll also define this in the limit where Q tends to zero. So in the sense that the test charge that we're talking about is a very, 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 very tiny test charge. Why do we want the test charge to be very, very tiny? We want the test charge to be very, very tiny so that it does not interfere with the electric field that is already there. Because we only want the test charge to test and not
Yes.
to change anything. That is why we want Q to be very, very tiny. What is the SI unit of this thing? Any idea?
Uh, no idea, sir.
फोर्स का क्या यूनिट होता है? न्यूटन. चार्ज का
The
क्या
new.
न्यूटन होता है? कूलम. तो न्यूटन पर कूलम. डन.
Okay.
Or you can also write it down as volt per meter. Um, we'll come to this definition soon when we're going to talk about potential energy and electric potential, which will essentially be driven from this particular field that we talk about.
This.
Okay. Okay. So let's talk about the electric field due to a point charge. The electric field due to a point charge. So as we know, if we have, let's say, a point charge capital Q, um, and there is a small charge small q which is at a distance some r away, the force which will be acting on small q because of capital Q, this is going to be k q over r squared. In what direction? R cap, right? Since both are positive, it's going to repel, so it's going to be in the outward direction. So that's why I'm writing it as positive r cap. Make sense?
Yes.
Now, using the definition of the electric field because of Q, this is just force divided by small q. So this is just kq over r squared r cap. So this is essentially how we write down the electric field. Let's see how the
Why have we taken R cap over here? Because it is in the direction of R.
yes, because it's only in the direction r. It's not dependent of theta. It's not dependent on any of the angle, is it? Is it dependent on the charge? It's dependent on epsilon, which is essentially permittivity, on what medium you're placing the charge in, and obviously the distance from the charge. And it always acts radially outwards in the r cap direction. Okay, so let's try to plot this and see how this looks like. Um, let's So let's say you have the electric field on the x-axis and you have x, or let's say the distance r. We've been using r, so let's continue to use r. Electric field we found out was looking like kq over r squared, right? So how does r square look like? The graph r squared, 1 by r squared, sorry. How does it look like?
Sir, 1 upon r square.
Yes. How does it look like?
Sir, a single curve.
Yeah, it will. Well, you will actually have two curves. But let's just talk about the first quadrant right now. Let's not complicate our situation even further. Let's talk about the first quadrant. 1 by r square का ग्राफ कैसे दिखता है?
Sir, positive, all positive
Yes.
in the first quadrant.
Yes,
And
it's all positive. So how do you essentially plot any graph? Very simple technique. Put,
the points.
yeah, 2 points. Put r tending to 0, put r tending to infinity, and check what is happening and just connect them. R tending to 0 pay, it's at infinity. R tending to infinity pay, it's just 0. So this essentially is how the graph is going to look like. It's going to fall, but it's going to fall faster than 1 by r. 1 by r, yes. So this is how it is. And if we talk about the negative r, or the backward direction, well, this is essentially going to look like this. Exactly the same thing here, but just flipped about a mirror, which is in the diagonal direction 45 degrees, 135 degrees. Okay, this is because of a plus q charge, right? What about a minus q charge?
Uh,
What about you have, let's say, a minus q charge?
so then the graph will go around the third quadrant.
Yes. So essentially, when you put r tending to 0, instead of going to plus infinity, this will go to minus infinity, and so this will essentially look like this, and here it will look like this. Does it make sense?
Yes.
So essentially, all the four quadrants are filled by using plus minus r and plus minus q. Make sense?
Yes.
This will be slightly important, but we'll see how. Now, now moving on, there is a superposition principle for electric fields as well. Superposition principle. So before this, we talked about superposition principle for the forces, and exactly through the same line of logic, because we already knew that the superposition principle works for forces. And since we've already defined electric field as just the force over unit charge, or a very small charge, superposition principle should also hold for electric fields. Essentially, what's the meaning of that? It just means that, let's say there are n charged particles, there are n sources. There is some charge q1 here, some charge q2 here, some charge q3 here, and let's say the charge q1 has a field, an electric field E1, which is equal to k times q1 over, let's say we're figuring out some r distance away. So q1 is, let's say, r1 distance away, q2 is r2 distance away, q3 is r3 distance away, and so on and so forth. So what you will have here, you will have k q1 over r1 squared, right? For q2,
Yes.
what will you have? You will have e2 q2 over r2 squared. And for Q3, again, you'll have E3, which is going to be K Q3 over R3 squared, and so on and so forth, up till Qn, which is essentially will have En, which will be K Qn over Rn squared. Okay. What the superposition principle says is that the net electric field at this point, P, let's call it, it's essentially going to be the electric field because of 1 plus the electric field because of 2 plus the electric field because of 3, and so on and so forth up till electric field because of n. Okay, very straightforward. Correct? Yes, no?
1 minute. So,
Okay, think about it.
so we will just have a numerical uh, sum of all the what do you say?
A vector sum. Notice
Vector sum.
a vector sum. This is a vector sum. This is not a scalar sum.
Yes, a vector of all the charges. Okay.
Yes. Yes. Okay, so let's do a couple of problems based on this exact same thing. The first question, you have two charges, plus E and let's say minus 2E, which are placed is at separation. Let's call the separation A. At what point? At what point the line joining the two charges, the electric field is zero. Field is zero. Does the question make sense? It's exactly the same question as was done in the previous class, the last part of this which we talked about.
So in this, one charge is plus E and the other charge is minus 2.
Minus 2E. Yes.
And they are placed at a separation of A.
Yes.
So we just had to find the point.
Where the
So the
electric
point
field
is
is
the
going to be
line.
zero.
It is given that the point is in between. Point is somewhat in between these two charges,
Yes, yes, yeah, absolutely true. How do you know that?
and an electric field will be zero.
So where is the electric field going to be zero? Let's assume that the electric field is going to be zero at this point. Let's call this point P. Let's say this point is at a distance of x away from E, and hence this distance becomes A minus x. Correct?
Yes, sir.
So now what's the electric field because of 1 going to be? It's going to be K E over x squared. Correct?
Yes, sir. K E over x square.
And the electric field because of 2 is going to be minus, because of the negative sign, 2ke because of the 2 here,
K upon x. A minus x whole.
whole square. Lovely. So let's add them together. What do you have? You have ke over x square minus 2ke over a minus x whole squared should be equal to 0. The k's cancel out, the e's cancel out, and what remains is 1 over x square is equal to 2 over a minus x whole square. Correct? Now simplify this. Simplify this further. And what do we get? Well, we get a minus x over x is equal to square root 2. This implies a minus x is equal to x root 2. This implies I'm taking the x to the other side. What do you get? X root 2 plus 1. And hence x is just equal to a over square root 2 plus 1. And if you multiply by square root 2 minus 1 square root 2 minus 1, what do you get? You get a square root 2 minus 1 over 2 minus 1, which is just 1. So it's just a square root 2 minus 1. Make sense?
Yes.
Any problem up till now?
1 minute.
Okay, think about it.
Uh, so we simply get that a root a minus a root 2 minus 1.
Yes, absolutely.
X is equal to a root 2.
Huh.
Done, sir.
Okay. So similarly, 3 points. So you talked about 2 points. Let's talk about 3 points. So you have 3 points. You have 3 charges also kept, plus q, and a plus q. Consider this to be an equilateral triangle of side A. Please find the electric field at a point O, which is at the centroid. Yes, yes, this is the centroid. O is defined as the centroid. Can you give a direct argument of whatever the answer is going to be without actually
Uh,
going ahead and solving it?
so we have to find uh, the charge at O,
No, no, the electric field.
the electric field at O.
Hmm.
X square is going to be the same. So, and E is also the same.
Yes. So
So sir,
since
I guess in the
since
end, because the directions are different, so if we resolve each of the direction into one single plane, they will eventually get zero.
yes, exactly. So since all the distances are equal,
And charges are also equal,
yes, and charges are also equal, the
but the
net force
directions
at
are,
the center, the net electric field at the centroid at O is just going to be zero.
yes,
Similarly, you can see that on a square as well, if you have four charges plus q plus q plus q and plus q, then at the
center is going
center
to be
it's
zero.
going to be the electric field is going to be zero. Similarly for a five-sided and for an n-sided
So
object as
polygon,
hmm?
any
Any
polygon
polygon up, and you can keep on going any polygon, absolutely correct, and you can keep on going, you can keep on adding sides until unless you get the infinite polygon or a circle, correct?
yes,
And the center point of the circle, the charge is going to be zero.
zero.
Sorry, not the charge, the electric field is going to be,
That's yes, sir. Charge is not.
yes, so the electric field is going to be absolutely zero. Lovely. So you can think of this as a trick as well. So whenever you're given a polygon shape,
Yes, sir.
you immediately know what the, the electric field is going to be at one particular point.
Yes, sir. For example, in a ring, the electric field at the center will be zero.
Absolutely correct. So you can use this as in a lot of different ways. Um, Okay, I think we should just stop here because next is a different topic altogether, which is the electric dipole. So we'll
Yes,
come to that next week. And so, yeah,
yes. Thank
let's. No worries, no worries. Any doubts today? Any problems? Any thoughts?